So, question 5 says design a soft clipping circuit that will realise the VO to VI characteristics of figure 5 using diodes that have a turn-on voltage of 0.7 volts. Base your design on the circuit of figure 3. Keep the 1 k ohm resistor and add a series resistor into each of the diode arms. Work out suitable values for V1, V2 and the 2 series resistors. Well, the circuit of figure 3, or the modification of the circuit in figure 3 that the question is asking us to do, looks like this. And we'll call that D2, we'll call this R2 and we'll call this V2. And we've got another one which is D1, R1 and V1. And then we had a series resistance and we had a voltage source as well. And this was VI. And the series resistor was 1 k, and we'll call this one R. Alright, so the characteristic that we're being asked to find looks like this. We've got VO here and VI there, and we've got that's 3 and that's 3, and we've also got -5 and -5, and we have a slope of 1/3 in the region past -5, -5, and then the region -3 to 3, -5 to +3, we've got a slope of 1, and then in the region past 3 volts we've got a slope of 1/2. So we've got two regions of clipping and one region of no clipping. So we've got one diodes conducting in this region to give us a slope of 1/3. There are no diodes conducting in the middle bit to give us a slope of 1. And we've got a diode conducting past V is 3 volts to give us the slope of 1/3. Both of these are in volts. So from the last time we looked at figure 3, which was in question 3, we'll remember that this diode D2 was dealing with the negative side of things, and that D1 was dealing with the positive side of things. So we'll start off with D1, and we need to figure out what we have to do to V1 to put D1 on the edge of conduction when V in is 3 volts. So that's going to have 0.7 volts across it, because it's diode, and we want. The other thing we're going to say, of course, is there isn't going to be any current. So that's 0 amps. And VI is going to be 3 volts. So, and of course, if there's no current in the diode, and we're assuming all this lot switched off as well, there's not going to be any voltage across the resistor because there's no current in it. And the same holds for R1, there's no volts there because there's no current in that either. So we've got 3 volts here, minus nothing, so that's 3 volts, minus 0.7 volts, so this point is at 2.3 volts with respect to ground, ground being all this stuff here. And then we've dropped nothing across the resistor, so 2.3 minus nothing, so we need 2.3 volts there. So across this source, we should have 2.3 volts, and that will give us our diode on the point of conduction when we need it. So first thing we can say is V1 is 2.3 volts. Then we have to deal with what the size of R1 has to be. Well, we've got some things that only fix this point of 3 volts, and then we've got some other things that vary, we can assume that the diode will always have 0.7 volts across it, irrespective of what we do, as long as it's conducting. I mean, however far we go that way, this diode will have 0.7 volts across it, and whatever we do, this V1 will always have 2.3 volts across it. So we can take them out of the circuit, and we can just deal with the changes that occur on this line. So we'll do a voltage source VI, a resistor R, which is 1K, and we'll have another resistor which is R1, and we know that we're looking for a situation. I'm sorry, I got that wrong. That's not a third. It's a half, isn't it? Yeah, it is a half. So we're looking for a situation where if I had, say, 1 volt here. Now, when I say 1 volt, I'm assuming this 3 volts is absorbed. So you could call it 4 volts if you liked, but I'm going to ignore the extra that we've taken away. I'm just going to say I'm using 1 volt here, and I'm only worried about the changes that are happening on this line. So if you like, this is a circuit that only deals with dy by dx in this region of diode conduction, and that's going to have to elicit a V out of 0.5 volt, because that's the slope of the line. Well, if that's the case, what we've really got here is a potential divider between 1K and an unknown resistor, and I want to get out half of what I put in. Well, half of 1 volt is dropped across here. Must be, because the other half a volt is dropped across here. If I've got half a volt here and I need to make 1 volt, all I can do here is put a half. So if this voltage and this voltage are the same, and the current that flows around the loop is the same, because there's only one loop, they're all going to have the same current, then whatever value this resistor takes, this one must have as well. So by inspecting the circuit, and I don't have to do any maths, although you could do the maths if you wanted to, you can say, just by looking essentially, that R1 must be equal to R, which just so happens to be 1 kiloohm. So R1 is 1 kiloohm. Alright, so that's the 3 volt point. We now need to look at the D2 arm of things. So I'm going to get rid of this for a bit. And I'm going to get rid of the majority of these green arrows as well. Try and tidy up the diagram a bit. Alright, so the process is exactly the same with the other arm. We're now going to say that I've got minus 5 volts here, and there's still no current flowing through this diode, and the diode itself is still on the edge of conduction. Or not still, this is the first time we've considered this diode, so this diode is on the edge of conduction, and I want to know what value of V2 I have to choose to make it so that when V in is minus 5, the diode is just about on the edge of conduction. Well, if that's 0 amps, we can go back to the same old, there's no current in there, all this lot's, don't have to worry about it, so it's not even, don't have to consider it at all. If there's no current in this branch, there can be no voltage across there either. So what we need now is I've got minus 5, minus nothing, so I've still got minus 5, and I've got 0.7 there, so this is 0.7 volts above minus 5. So minus 5 is the lower voltage, and we go 0.7 volts upwards from -5 and upwards is less negative. So this point here is going to be at -4.3 volts. Now, I've got no voltage across this resistor either, so this one's going to have to be at -4.3 volts too. And that happens to be the voltage across the source. So the V2 value must be -4.3 volts. So I can write that down as well if there's any room. V2 is -4.3 volts. So the only thing I've got left to do is to figure out what R2 needs to be. So I can do the same thing that I did before. I can draw out a little diagram that only worries about the changes in this region here. I don't have to worry about the 5 or anything, I'll just work on the dy by dx in the region of the diode being switched on. So I can get rid of the 0.7 and the 4.3 and worry only about the changes in voltage. So we'll have a V in and we'll make that a volt. Doesn't even have to be negative. Don't have to worry about that. And this is RS and this is R2. And what we want out here is a third. So we're in a situation now where we've got a volt in and a third of a volt out. So we must have 2/3 of a volt there. So you can say, well, if this is 1 kilo ohm, 1 kilo ohm is worth 2/3 of everything, and something else is worth 1/3 of everything. Well, if 1 kilo ohm is worth 2/3 of something, 2/3 of something we don't know about, then the thing we don't know about must be 1.5 kilo ohms. And if that's the case, then if everything we know about is divided up in the ratio of 2 to 1 between RS and R2, then R2 must be 500 ohms. It's just a potential divider. If you want to, if you don't like that, if you think that's magic or not allowed, then the other way you can look at it is to say, alright, what we'll do then is we'll say that, call this V out, we'll do V out over V in is equal to R2 over RS. I just called it R over there, didn't I? S. Plus R2. And you'll say, right, I'm going to get R2 out on its own, and you know that all this stuff here is worth a third. So we've got a third is equal to R2 over RS plus R2. So we'll do RS plus R2 over 3 is equal to R2. So then we'll do RS plus R2 is equal to 3R2, and then we'll do RS is equal to 3R2 minus R2, so RS, come on that man, RS is equal to 2R2. Now if RS is a kilo ohm, then 2R2 is a kilo ohm, so R2 is equal to 1K divided by 2, which is 500 ohms, which is the same as what I got in many less lines of work and a little bit of thinking. I can get rid of this as well now. Well, that's the only thing that's left to say. Is that R2 is 500 ohms, and that's the circuit designed.